a Lie algebra valued one form such that its flatness, which is this equation here, for all values of this parameter, complex parameter u, which we call the spectral parameter, is equivalent to the equations of motion. On the other hand, some years ago, Costello, Yamazaki, and Witten introduced this four-dimensional Chern-Simons theory, which is essentially a two-dimensional integrable field theory builder. So it's a theory that lives on R2 times CP1. And so R2 is going to be interpreted as the worldsheet, and CP1 is the space in which the spectral parameter U lives. And in this construction, you input a gauge group, some defects on CP1, you use the 4DCS machinery, and then it spits out a two-dimensional action and a lexicon action, and then we have an integrable field theory. An actual question then is, can we perform this construction on the pure spinor? We can construct a pure spinor superstring in AdS5 S5 with this four-dimensional Chern-Simons theory. Let's see. So just a quick review of the pure spinor superstring in AdS5 S5. It is a super-coasted model defined on this coasted here, and we construct the action out of the G-1 DGs, the Morrow-Cartan currents, and we can use the Z4 gradient of the PSU224 superalgebra to decompose the Morrow-Cartan currents in terms of these four other fields, and we use them to construct the action. So this first line is what we call the matter action, because it's constructed out of the J's. And the second line is the ghost action. In the pure spinor formalism, we have this ghost lambda here, which we call pure spinors because they satisfy these constraints down here. So in this Lie algebra language that we can use in AdS5, they anti-commute with themselves. And this AND field here is just an anti-commutator with the anti-ghost and the ghost. Nothing fancy. Now we define the four-dimensional Chern-Simons theory, and I'm going to tell what defects we need to introduce in CP1 to construct the desired model. So it is just a usual Chern-Simons action. We have here the Chern-Simons tree form, but since we are integrating in a four-dimensional space, we need to edge it against a one form. For now, we choose this one form DZ. It could be other holomorphic or meromorphic form on CP1. And as a gauge group, we naturally choose PSU224. And from now on, W and W bar are the coordinates on R2, and Z and Z bar will be the coordinates on CP1. And so to perform the construction, we need to introduce a line defect on CP1 such that the gauge field A is actable upon with this automorphism of the algebra rho, which is essentially the automorphism that induces the Z4 gradient of the PSU224 algebra. And so it acts as such in the subspaces related to this grading. To better understand this defect, we need to go to a fourfold cover of CP1, which we call the U-plane. It's defined by this change of coordinates. Of course, the one form also changes under this change of coordinates. And now note that we have poles at each of the fourth roots of unity here. This is going to be important. Moreover, the line defects map to these lines connecting u equals 0 to u equals infinity. So if we want our gauge field to be single-valued under this non-trivial monodromy induced by the line defect, it needs to satisfy the following constraints. So from now on, we are always going to consider gauge field configurations that satisfy this constraint. Moreover, because of the poles of this one form, which we call omega from now on, we need to introduce Dirichlet boundary conditions on the R2 components of the gauge field when we are the poles of the one form. Okay, so now let's see how we can go from this four-dimensional theory to a two-dimensional theory. We start by gauge fixing. First of all, we'll try to gauge fix AU bar. We'll try to gauge the AU bar component of the gauge field away. If we can do so, then it is possible to write the gauge fields in this parametrization here, where L will be the gauge field that is left after this gauge fixing. It is, of course, a one form along R2. But because of the boundary conditions, it turns out that we can gauge AU bar to 0 everywhere. When we are near the poles, this is not possible because the gauge parameters need to be consistent with the boundary conditions. And so then this leads to 4 group value degrees of freedom, one living near each of the poles of the one form omega. But these are actually not 4 degrees of freedom, but only 1. Because due to the single valueness condition, all of these G fields are related by the automorphism rho, by this equation. And so after this gauge fixing, we are left with the field L and this g-value degree of freedom, which of course will be our matter variables of the sigma model. But the ghosts are still missing. How can we get the ghosts? We need to look at the residual gauge transformations after we perform this first gauge fixing. To understand them, let's look at the equations of motion for the gauge field L. The first equation of motion just says that we have poles up to third order at u equals 0 and u equal infinity in L. This is so because omega has third order zeros at those points. The second equation is just the usual flatness equation, and it means that we can interpret this L field as the Lex connection. Perfect. The residual gauge symmetry just looks like a usual gauge symmetry, but the gauge parameter lambda tilde needs to have a special form. It has this meromorphic dependence on the spectral parameters. And moreover, note that the dependence is such that these parameters vanish at the poles of the 1, 4 omega when u to the 4 equals 1. We can use this gauge symmetry to impose gauge fixing conditions on the pole structure of L, since they are have meromorphic dependence on the spectral parameter, and we'll use it to impose that LW is regular at u equals infinity and LW bar is regular at u equals 0. This will lead to these sets of ghosts here. Each ghost is related to each of these parameters. You could argue, but Rodrigo, what about these higher poles? It turns out that these higher poles are non-independent, so the only independent gauge parameters are these first three, and so this is the correct sets of ghosts. And we can do a BRST procedure and use some cohomology arguments to show that these sets of ghosts with this the BRST charge that we get is actually equivalent to a system of a pair of pure spinor ghosts with the BRST charge of the pure spinor formalism. So, okay, we have all the ingredients now, the matter fields and the ghosts. So this is the final picture that we have. We have this big CPU1 here with the matter fields living at the poles of the 1 form omega, and the ghosts are living at u equals 0 and u equals infinity. They live in these special points because we have imposed gauge fixing conditions on the gauge fields, of course, at u equals 0 and u equals infinity. Therefore, they are localized. And the equations of now we need to analyze the equations of motion for L with the ghosts present. Note that they act like sources for the gauge field L. And what is left to do now is let's look for the solution for these equations of motion, of course, consistent with the single valueness constraint, the boundary conditions, and the gauge fixing conditions that I have imposed. So these two equations of motion imply that the poles of L, so L needs to have a fourth order pole proportional to n, and LW bar needs to have a fourth order pole proportional to n hat at u equals infinity. And of course, this fourth pole needs to be at u equals 0. Okay, and the only solution to these equations of motion is the solution here, which is actually the Lex connection for the pure spinor formalism in AdS5 S5, so that's great. But even more, we can plug this back in the 4D Chern-Simons action and actually show that we retrieve the correct two-dimensional sigma model for the pure spinor superstring in AdS5 S5. So now for some quick conclusions. So this means that we have completely embedded the AdS5 S5 pure spinor formalism in 4D Chern-Simons theory. Therefore, one could say that its integrability is natural, as it is granted from the fact that we constructed it out of a 4-dimensional Chern-Simons theory. Moreover, the pure spinor ghosts, which we usually regard as somewhat mysterious, they come from usual gauge fixing and Fadeev-Popov procedure in this framework. And some questions and perspectives are that maybe we can try to relate this construction to the one that Bogdan and Kevin did for the Green-Schwarz superstring in AdS5 S5. That would be interesting. And it would also be interesting to see if this can aid this framework can aid us in better understanding AdS5 S5 superstrings at the quantum level from the worksheet. And that's it.
Perfect.
Thank you.
Rodrigo, wonderful. Perfect timing.
Yeah, I had a...
Perfect. So, one question.
So there are many other integrable deformations, for instance, or other integral background, AdS4, AdS3, eta deformation, lambda deformation, so on. Do you think this will go through for all of these, or there is some obstruction that you can foresee?
No, I think it should be possible. People have done it for the matter part of the sigma model. You need to change some boundary conditions, change the defects a little bit, and you can get some integrable deformations. But it would be interesting to see what this implies for the ghost system. This haven't been done, as far as I'm concerned. And thanks for the organizers. Didn't have time to.
Strategy. Thank you.
Okay, so now our second race. Ana Lucia Retore will be talking about elliptic deformations of AdS3 times S3 S-matrix.
Okay, thank you very much for the organizers for giving me this opportunity and for putting this, organizing this very nice meeting here in São Paulo. So I will talk about a project that we finished in December with, the first part with Fiona Seibold and Ben Hoare in Durham. And this is about elliptic deformations of sigma models, string sigma models. So as we discussed here, we believe that AdS3 times S3 times T4 world sheet S matrix is integrable. And actually, if you look at it, the full S matrix satisfies the quantum Yang-Baxter, but actually, it factorizes like this. We have to something like 2 blocks, but it also in each of these parts here in the factorization actually can be written in blocks like this. But what happens is that these objects satisfy Yang-Baxter, but also actually each of these satisfy Yang-Baxter, and these satisfy Yang-Baxter. So there is a lot of integrability appearing, like a lot of Yang-Baxter appearing here. And in particular, like these 4x4 blocks, they are of 6 vertex form in the case of AdS3. And in a sense, they are similar to XXX R matrix. But there are also deformations of these S matrix. For example, a trigonometric deformation, so a Q deformation. It's still a 6 vertex object, but now you have a deformation parameter. And for this trigonometric case, you also have all this decomposition structure, like this factorization, the blocks. But in a sense, it's more similar to XXZ. So one question we would like to answer is that, what about an elliptic deformation of strings in AdS3 times S3 times T4? So in the same sense that in a spin chain, we would have like a Q deformation, but also an elliptic deformation, can we do something similar here? And from a completely different point of view, we found one. So when I was in Dublin with Chiara, Marius, Anton, and Paul, we found this deformation. So it's an 8-vertex object. I just wrote one of the matrix elements here, so it depends on Jacobi functions. But an interesting thing is that when you send the modulus of these elliptic functions to 0, we actually recover AdS3 times S3 times T4 S matrix. Okay, I'm ignoring the dressing phases for all what I'm saying here, like just thinking about the matrix part. And just as a curiosity, if you send k to infinity, it actually goes to the AdS2 one. But the point is that this is quite nice. In a way, you can write the blocks, the factorization, you can define the big one, and everything satisfies Yang-Baxter and follows. And you can write some crossing equations that seem to make sense, although we didn't solve them. But we found these. We were trying to classify solutions of the Yang-Baxter equation. We were not thinking about the AdS3 when we first found these. So we came from a completely different direction. So a natural question is that does this actually make sense? It comes from a string sigma model. It's just a coincidence that we can embed all these things there. So that's the question we have been trying to answer with Ben and Fiona. So I will be very schematic here. I will start by focusing only on AdS3 times S3, and at the end I will make some comments about the T4. But the steps are basically, you take the principal chiral model for this algebra. That would be what you do to get the undeformed case. And we write some elliptic deformation. So from the Green-Schwarz action, we can read that the B field is 0 in this case, and this is the metric. So it looks ugly. Don't look too many details, like what these alphas are just the deformation parameters in AdS. These ones are, the betas are in the sphere, and then the metric is just the sum of these two. But what do you do? So the only thing you need to look here for now is that the only isometries we have, the only shift isometries we have are in T and phi here. So usually in Green-Schwarz formalism, when you want to fix, to quantize, you fix light cone gauge, and you need some isometries to do that. So it seems like we deformed elliptically, and we still have isometries to fix the gauge. So that's good. And then after this, we can decompactify. So we take the radius of the cylinder, Orchi cylinder to infinity. We can define asymptotic states and compute perturbatively the S-matrix. So what we did was to compute the 3-level S-matrix. And well, this looks ugly. The dispersion relations are not great. So we expected some kind of very bad results. But at the end, we had a very big surprise, which was the S-matrix is diagonal. The 3-level S-matrix is actually diagonal. And this is very strange, because if you look here, after you fix the gauge, you don't have the T and phi here. There will be no isometries left on the transverse direction. So there is no global symmetry that seems to be on the Lagrangian when you look at, but somehow this one symmetry is there on the S-matrix. So, but it's diagonal, so it automatically satisfies the Yang-Baxter, so it's integrable so far. But then we tried to bootstrap the fermionic part. So we said, oh, we know the bosonic part. Let's assume the factorization is there, the block structure is there, and let's try to find the fermionic part, just see if it's possible to find something that would satisfy the classical Yang-Baxter. So a 3-level S-matrix that satisfies the classical Yang-Baxter, and it turns out it's impossible. So we basically, now we have like some nice supergravity background, and we are at the moment trying to compute the 3-level S-matrix. But once we have it, we should be able to at least understand what is actually happening, because we assume this factorization in the block structure to do that check. So it could be the factorization will break. It could be this block structure would break down, but it could be that it actually just breaks integrability. But a fourth option that is kind of interesting is that it could break integrability in a very controlled way. So what we know from this model that we found in Dublin, this exact S-matrix, is that it's a deformation of the undeformed AdS3 times S3 times T4, but not of the Q deformation. To get the Q deformation, we need to twist it first. But if you do the twist we need to do, you break integrability. So you get this Yang-Baxter with all the twists. So you get this different Yang-Baxter. So what we think it could happen is perhaps you need this twist there. So there is the breaking of integrability to satisfy this Yang-Baxter that is not co-associative like this kind of. But to know that, we need to finish and compute the S-matrix. This is what we are at the moment doing. And then once we have the 3-level, so in the trigonometric case, what happened is that once you have the 3-level, you could look which symmetries you had, and actually there was a hidden quantum group symmetry there that you could use to bootstrap the full, like the exact S-matrix at all orders in the inverse of the tension, of the string tension. So one question we would like to understand what is actually happening, but we also would like to understand if there is a hidden symmetry, like some type of elliptic thing that would help us to actually bootstrap the full exact S-matrix. And then a further question is that, well, like if if we go back here, if what's happening, oh, what time did I do? Oh, yeah. If what's happening is not this fourth option, then this model is not the model we found in Dublin. And then we still don't know if that comes from Sigma model or not. That's an option. But so that's a next question. Then we would have to try to look for something else, and we don't know what that would be. But yeah, we need to first finish these, and then hopefully we can answer these questions. So, and I went far too fast, but thank you very much. Much faster than the practice.
Okay.
I will not have the sound now. That's.
It's okay. We can ask more questions. Then. But suddenly, I think the music will appear.
Thanks for a very nice talk. I thought that classical integrability of the three-level S-matrix is basically equivalent to solving the equations of motion. And once the equations of motion are integrable, then the S-matrix should be integrable. But isn't it guaranteed?
I don't see how that's, because when what we did here, we fixed like on gauge, and then we have Lagrangian like L2, L3 is 0, but then we have the interacting Lagrangian L4, and that's not so we use that to compute the S matrix. So, and that is diagonal, so it's automatically, so so you are saying that any classical should satisfy Young-Baxter? Yeah, I think that's.
I think so, because the three-level S matrix only carries information about the classical equations of motion.
That's true, but. I'm confused now. Can we talk? It's a very simple question, but now I just blank. Thank you. Yeah.
Small question.
What's wrong if it's just diagonal even when there are the fermions? I mean, you said that there is no solution that satisfies the classic Young-Baxter, but clearly remaining diagonal is fine. At tree level, not in general.
At tree level, but we already know that the trigonometric, when you include the fermions, has something, right, on the off-diagonal.
At tree level?
I think so.
Okay.
So that was the, so if the trigonometric already does, the elliptic for sure we would be, because this case we are doing it always reduced to the Q deformed when the parameter, like alpha 2, like when the parameters, two of the parameters are the same. You can talk.
Well, okay, so we have things to discuss after the next talk. Thank you,
Thank you,
Ana Lucia.
Like this? Okay. Okay.
Perfect.
What about
Is it okay?
the
Pointer?
pointer?
Try this. And if not, no, this.
This one?
This
Okay.
one. You have to point there to change the pages.
There, upstairs. Okay.
Yes. Okay, so our next speaker is Lucas Martins. He will be talking about SU2, 2 times SU4, covariance in AdS5 cross S5, pure spinor formalism. Lucas?
Okay. So first I review pure spinor formalism. So let's start. So the pure spinor formalism was established by Hall in 1991 in the context of supergravity. The central object is a fermionic vector field in appropriate loop superspace. For example, in type 2 supergravity, this vector field is given by equation 1, where alpha and alpha hat are Majorana-Weyl indices. This nabla here denotes a covariant derivative, and it's important that it's defined in loop space so that the B field is incorporated. The variables lambda and lambda hat are the pure spinors, of course, along the loop. And they satisfy a constraint given by equation 2. This constraint is SO 1,9 invariant. Okay, so the supergravity equations of motion come from imposing new potency on the vector field, given by equation 3. In particular, this equation governs the back-reacted geometry of fluxes. So as soon as you turn on fluxes, this equation is going to give you how metrics should behave. So scattering states are characterized by the cohomology. So yeah, solving equation 3, you get a background, and then you can compute scattering states about this background. And that's what equation 4 gives you, which is a cohomology of Gauss number 1,1. By 1,1, I mean the dependence on the pure spinor variables. So you can think about those pure spinors as differentials in loop superspace. So this formalism can be extended in the worksheet, and this was done by Nathan Berkowitz, as everybody knows, of course. And it's schematically given by equation 5. So I just wrote the important pieces of the action, and this dot 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 can include curve background deformations. So the pure spinor variables are like beta gamma systems, but curved beta gamma systems because lambda are constrained. And the fermions, you get this funny D and D alpha, which you don't get in Green-Schwarz. And those those variables were introduced way before pure spinor formalism by Siegel in 1985. Okay, so the pure spinor formalism has the advantage over the Romanov-Schwarz and the Green-Schwarz in that the worksheet action is quantizable and manifestly supersymmetric. In particular, the Romanov fluxes can be easily coupled to the worksheet action given by equation 6, where eta alpha of a hat, which is the first term in equation 6, is a Ramon-Ramon bispinor. It encapsulates all the Ramon-Ramon fields by coupling with gamma matrices. In the presence of an invertible Ramon-Ramon flux, one can eliminate the Siegel's variables because you get a quadratic action for the D hat. So you can integrate over D, and then you get something like equation 7. Okay, so now we review pure spinor formalism. We will now focus on the background generated by the 10-dimensional self-dual Ramon-Ramon flux, namely AdS5 cross S5, and proceed to eliminate Siegel's variables d alpha and d alpha hat. So the subgroup of SO1,9 that stabilized self-dual Ramon-Ramon flux is SO1,4 times SO5, and the back-reacted geometry is a coset. It's given by equation 8, where SO4,2 and SO6 are the isometries. The respective spin groups are given by equation 9, so you get special unitary matrices, and you get special unitary symplectic matrices. It seems special, it's just symplectic unitary matrices. So using those symplectic unitary indices, the pure spinor constraints which you saw before is given by equation 10. And these epsilons here, they are symplectic metrics defining the subgroup of SU2,2 times SU4, and they correspond to fixed space-time events. So in 2008, Berkowitz and Waffa proposed a two-story description in which the closed-set parameterization are contracted against the pure spinor variables given by equation 11, and enclose the 10 space-time coordinates and 22 pure spinor components. So the pure spinor constraints translate in this language of Berkowitz and Waffa to equation 12, where x and y are essentially the coset contracted with the epsilons. And because of that, they satisfy equation 13. And equation 13 tells you that the AdS5 cross S5 is embedded in 12 dimensions. So now we end up with SU2,2 times SU4 covariant variables together with SU2,2 times SU4 invariant constraints. So had we started with SU2,2 times SU4 covariant variables, x, y, z, and z bar, together with the constraints, the group elements v and u would have appeared as SU2,2 times SU4 compensators. This is because in the presence of the compensators, they are not just SU2,2 times SU4 isometries that rotate the R and I indices, but also the SU2,2 times SU4 gauge invariances that rotate R tilde and I tilde. These gauge invariances can be used to remove the compensators or to gauge fix the axis, as I did here in equation 15, to epsilons, which returns to our starting point. So because of the constraints, x and y are both invertible matrices, and one can change bases in the spaces spanned by z and z bar, which is given by equation 16. Some of the pure spinor constraints are mapped to equation 17, where those parentheses are just contraction with lambda and lambda bars in the most obvious way, and then you remove the traces. Okay, using the SO6 and SO4,2 Pauli matrices for the SU4 and SU2,2 indices, I can isolate the traceless part. With a bit of thought, I can conclude that these lambda bar variables are constrained, given by equation 20, which follows from 21, which is just a translation of equation 17 to SO6 and SO4,2 notation. So because of the constraints, Z and Z bar have fewer than 32 components, so they cannot encode both 10 space-time coordinates and 22 pure spinor components. In other words, this equation here is not invertible. So moving in the opposite direction, Mikhailov and Shu in 2013 solved the pure spinor constraints by gauge fixing the USP 2,2 times USP 4 down to GL1 times GL1. One first breaks one of the symplectic groups, ignoring reality condition for now, by fixing one of the pure spinors, give equation 22. This pure spinor is fixed to be proportional to the identity, and then the remaining gauge, residual gauge symmetry were used to gauge fix the lambda hat to equation 23. Then there is a residual GL1 times GL1 symmetry group that preserves this lambda hat, which consists of the elements of USP4 diagonal that acts on both indices, two types of indices. The form of this GL1 times GL1 is given by equation 24, and one can eliminate all the 20 components of the projective pure spinor, so not the ghost part, just the part about respective to the spin, together with the 10 space-time coordinates in favor of the 30 components of the SU2,2 times SU4 compensators, simply by gauge fixing the GL1s, A equals ni1, B equals ni2. Conclusion, so given the constraints on the proposed two-historical variables, which prevent them from encoding AdS5 cross S5 space-time coordinates, together with the pure spinor variables, we leverage the residual gauge symmetries. This enables us to encode the AdS5 cross S5 together with the projected pure spinors into SU2,2 times SU4 compensators, given by V and U. So the next step is to search for gauge fixing that will extract these 30 components from the compensators and map them into unconstrained SU2,2 times SU4 covariant variables. And I will end it here.
Very well. Thank you, Lucas. Questions? Kolya?
So do you believe that in this formalism is complete at the quantum level, or you need to...
No, I don't believe it's complete at the quantum level. That's why I'm doing this, yeah.
More questions? Okay. If not, we thank the three speakers for perfect timing.